Hi, my name is Neeley, and that's Dru Doelling. We are the Meta. Week 6, group problems. Here we go. Okay, so number 1 up here. Disease and blah 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 that affects 100 or 1 out of 150,000 individuals. So right away, I took 1 over 150,000. I put it right here. This is the way we like to set them up, as I feel like Kelson taught us. And it's really easy. So here's 1 over 150,000. Put that right in the recessive. Now to get here to the recessive allele, you just take the square root of this, put that over here, then subtract it by 1 to get the dominant allele, and then you square that, and you get this, and you take the sum of these two numbers, and then subtract it by 1, and you get that. Now that is like the easiest way to do it. It's foolproof, and as soon as you do that, you just get all those numbers right there. What is the frequency of the D allele? Well, okay, that's right here. And what is the frequency of the dominant D allele? That's right there. What is the frequency of the homozygous dominant? Right there. And D, what is the frequency of the heterozygous? And that's right there. So all that really quick is boom in those charts. Now that you get to, use my laptop if you want to.
All right, so question 2 is fill in the blanks. The term Heisenberg equation represents the frequency of IB allele is Q, and then the term Heisenberg equation represents the frequency of the IB gene is 2P2. And D, the syndrome of autosomal dominant disorder is 1 of 1,000 of 24,000 individuals. The population affected by the syndrome is represented by P squared and 2PA. For C, the equation refers to the situation presented in part B. The 3,999 and 4,000 individuals is a population unaffected by the syndrome is represented by the P squared. The type of plumage found in ducks is determined by the 3 alleles, a single lotus. The restricted phenotype is dominant over Millard and Dusky. The Millard dominant over Dusky is that the R term is in the Hardy-Weinberg equation, but best represents the frequency of the MD allele. For E, this question refers to the situation presents an N. The term P squared, 2PA, and 2PR terms in the Heisenberg equation can represent the genotype of a duck with restricted plumage. For F, human disease, mystical cell anemia. For G, the term that best describes a trait is monophoric. For H, the name for a local population is genes, I think it's called. And then the genes in human are highly MHC genes are in humans are highly polymorphic.
Cool. All right, so moving on to 3. Perfect. All right, so 3, same exact pattern up there. So we've got 1 in 6,000 have the autosomal dominant disorder. So that means 5,999 have the recessive. So off of that, you just take 5,999 divided by 6,000. You get the recessive homozygous frequency. And once you have that number, it's super easy. You take that, the square root of this, you get that allele frequency. So 0.9999. And subtract it from 1, you get 0.201. Right? And you get the homozygous dominant, you just square that, you get that number, pretty tiny number, and then you just add these two together and you subtract it by 1 and you get heterozygous. And very, very easy. So then A, you just look at your chart. What is the frequency of the non-disease allele in the human population? Well, non-disease allele, that's lowercase m, so that's 0.999. B, what is the frequency of the Bavarian syndrome allele in the population? It's a big one. So we got a 0.0001. What is the frequency of the heterozygous individual in the population? Well, it's a heterozygous. Right there. Right there. And then D, out of 5 million people, how many heterozygous are expected? So all we have to do is just take our frequency, times it by 5 million, and we get 9,500. Very easy. Back to you, Drew.
Alright, so 4, it's a little tricky. You have to find the R2, and then you gotta find pretty much separate. You gotta find R2 and R3, and R3 has a separate too. So they find separate alleles. So we had the original and expected values we found. So what we did is we just did 135 plus 135, which is 2 of them, plus 44, which is right here. So ours R2, and we got 314. And what we did for the first column, we divided by 390, so we got 0.263 for R squared, or R2s. And then for the second problem, this is 11, sorry. What we did is we tried to find R3, so we did 11, so right here, 2 of them, 12 plus 11 plus 44, right there. Then you divide by 130, sorry, 390, sorry, we got 1.1736. And then for question 2, we had to do this. What is it? Hold on.
So we squared the allele frequency to get the
Oh, that's right.
homozygous
Square. Yeah.
dominant.
Dominant, and then there's an R2, R3. So do that squared.
No, so
Square
that
by
was
2.
yeah. So not quite yet. So we squared this one, and we add those together and we subtract 1.
There you go. Awesome. And this, all right. And then what we did for our last problem is that we had to try to square everything. So we did 135 minus 130 divided by 130 squared plus 44 minus 55 squared divided by 55, and 11 minus 6 squared divided by 6. We did that. We got 6.12. 6.21. For our conclusion, we said we rejected null because the changes in evolution is occurring. Pretty much.
Perfect. Moving on to 5. 5 is fun because there's 4 different alleles that are possible. So right off the bat, it gave us the 4 allele frequencies. We've got CCH, CD, CB, and the C frequencies right here. And so what I do, what we came up with was all different combination possibilities for this, and it's CCH, CCH, CCN, and because all these add up to 1, and all these add up to 1, you just kind of use the Hardy-Weinberg equations to figure this out. So for any of them that are the same, like heterozygous, so C, C, H, you take 0.37 and square it to get 0.1369. So all these you can square and just fill them in the blanks. Let's get one like CCHD. You would take the CH, so 0.37 times times CD, which is 0.23, and you multiply those by 2 because there's 2 heterozygous possibilities, and then you just fill in the blank. So we went ahead and we fill out all those stripes so we can answer the questions. What is the frequency of CCH, CCH, and CBC, and CC genotypes? So let's just go ahead and circle. So the CCH, boom, that one right there, there's the answer. CBC, CBC, right there. Actually, I'll throw them all down right here. And CC, right there. So those are our answers. B, among the population of 2,000 dogs, how many would you expect of the pale gray phenotype yet be heterozygous? So pale gray phenotypes is CB. So let's look at the CBs. Which ones are heterozygous? So it would only be this one. This is the only CB. So you just take that times 2,000. You get 150 right there. C, of a population of 5,000 dogs, how many do you expect to have white coat with dark eyes phenotype yet be heterozygous? So white coat with dark eyes would be CD. So we take the CDs, and we take the ones that are heterozygous, maybe these two, add those together, and then you times that by 5,000, because both of these will have the same phenotype. And then you get 3,112.5. That is how you solve question 1. Cool. Thank you so much, and see you next week. Okay, you guys take care.